IEEE Computer Society's Sidney Fernbach Award honors the memory of one of the pioneers in high-performance computers. Established in 1992, the award is given to an individual in recognition of outstanding contributions in the application of high-performance computers using innovative approaches. The 2022 IEEE Computer Society Sidney Fernbach Award is presented to Dr. Torsten Hoefler, a professor of computer science at ETH Zurich. He is being recognized for application-aware design of HPC algorithms, systems, and architectures, and transformative impact on scientific computing and industry. Dr. Hoefler and his team have been instrumental in developing techniques to improve the efficiency of high-performance computing and large cloud data center systems. Many of the developed ideas form core components for constructing, running, and programming supercomputers such as the ALP system, set to come online at the Swiss National Supercomputing Center in spring 2023. His work includes a focus on improving the performance of highly scalable parallel systems and developing numerous applications in the areas of weather and climate simulation and machine learning. His contributions range from hardware and systems design for HPC to middleware, applications, as well as algorithms. Dr. Hoefler won Best Paper Awards at SC conferences in 2010, 2013, 2014, and 2019, and at other international conferences. He has published numerous peer-reviewed scientific articles and authored chapters of the MPI 2.2 and MPI 3.0 standards. He received the ACM Gordon Bell Prize, the IEEE Computer Society TCSC Award of Excellence, and a Siam Junior Scientist Prize, among others. He is a fellow of the IEEE.
Everyone, please help me in congratulating the 2022 Sidney Fernbach Award recipient, Torsten Hoefler. Congratulations. It's my pleasure to announce our next speaker, the winner of the IEEE Computer Society Sidney Fernbach Award, Torsten Hoefler.
Thank you very much, Bill, and thank you very much to the whole supercomputing community for providing such a great environment for young scientists like me to strive in. I want to start with okay. Well, if that would work, then I would like to start. Okay, perfect. I want to start with Sidney Fernbach. So Sidney Fernbach was a great person, a great scientist, and he actually studied physics with Oppenheimer. And shortly after graduating, Edward Teller called him up to work at Livermore to install the first supercomputer in Livermore, the UNIVAC 1 machine. And that was more than 70 years ago. So this machine was actually quite a remarkable machine. It was one of the fastest on the planet at the time, but it was also small enough that 4 people could just push it into the back door of a computing center while one was standing there with their hands in the pocket. So it was actually quite an interesting architecture. Imagine that today. It's not possible anymore. So this machine had 5,000 vacuum tubes, and Sid Fernbach's job was to make this machine work for real scientists, for real science, to perform simulations on these 5,000 vacuum tubes with a team of mathematicians. So Sidney Fernbach at the end was really developing much of the foundation of what we know today as supercomputing and high-performance computing at the time. He did this by working at all levels, software, hardware, programming, and systems, because at the time there was no differentiation between those levels. That only crystallized later. And he was, of course, like many of us, always standing between the tension of vendors with some solutions, users with some needs that didn't always match the solutions, and technology that was since then going on a crazy ride, as we know, as Jack told us about, to where we are today. And actually, Sid Fernbach was a big fan of the machines that Jack talked about in the very beginning of his talk, these vector machines. So like the CDC and the STAR machine. And actually, towards the end of his career, he was even making these statements like we are seeing here that he doesn't really believe that massively parallel architectures are moving forward and are actually programmable and usable. And I want to specifically thank George Michael for recording an interview with Sidney Fernbach that I'm sourcing all of these quotes that you see on the following slides, this one and the following slides from. So really, he was talking to his friends when he tried to understand what architecture would be the right architecture to choose. And one of his friends was, of course, Seymour Cray. And Seymour Cray had the statement that all of us have probably heard, or the quote that all of us have heard, that turned into a meme at the time. Well, the meme in 1991 was a newspaper article before social media. So the meme was the chickens and the oxen. We all know about this. And the question is now, well, who won? The 1024 chicken or the ox? So what do you think? Well, we'll hear about this. Actually, I'm claiming that none of those won, because we haven't seen the billions of fleas in the background of this picture that were competing and actually won at the end. Just to give you an example, for the 2019 Winning Gordon Bell Prize, we orchestrated more than 91 billion logical GPU threads running on 37 million GPU or CUDA cores distributed across more than 27,000 MPI processes. So the question is now, how did we solve the Fernbach challenge, where he was saying this is impossible to program? But eventually, as we've seen in Jack's talk as well, we ended up as a community to support all of this, to run billions of threads and coordinate those on tens of thousands of machines. So I really want to go through my journey through this most amazing community together with you all. So why did I choose fleas to represent threads? Well, you know, these are these little insects that are quite annoying, right? They bite, they suck your blood. And as an HPC programmer, which many of you are, you probably relate to this. So if you orchestrate billions of threads, they really do these things to you. Furthermore, they're much easier to orchestrate than chickens, because even in the beginning of the 19th century, we had the flea circus going around, so industrious fleas. So we now arrange these fleas into warps, or threads. We take these warps into thread blocks. We move these thread blocks into kernel grids, and we all know how to program GPUs. We move those, kernels are invoked from operating system threads, and operating system threads are living in larger entities, MPI processes. I don't want to talk about the left side, because I believe Satoshi is going to cover that well in his talk. My métier is more the right side of how to run millions of MPI processes. On the left side, there's also millions of entities that eventually multiply together. So when I'm talking about running millions of processes, I have to actually go back again to 1993, the early days where MPI-1 was founded, or MPI-1 was created, with a great team of researchers at the time. And I want to again acknowledge Jack Dongara and thank him for being such a wonderful lighthouse for the community, including myself, to follow and look up to. MPI-1 was a standardization of existing practice. Shortly after, MPI-2 followed, and MPI-2 was an extension of existing practice. Then I entered the game, invited by Jeffrey Squires at the time to Andrew Lumsdane's lab. Unfortunately, Jeff Squires left the week before I arrived to Cisco. But fortunately, Andrew Lumsdane gave me the full freedom to do whatever I wanted at the time. So he basically told you, well, you're here, you can do whatever you like. And I looked at the major technology shifts in networking that were happening. And then 10 years later, after the MPI-2 specification, the MPI forum again reconvened, trying to understand how to react to these technology shifts. With a new and old set of people, many of those are now my dear friends. Then we moved on to standardize MPI-3, and later the forum moved on to standardize MPI-4. So I want to focus on MPI-3, where one of the contributions there is non-blocking collective operations, which are extremely simple. So let me just quickly summarize those. If you have P processes, these P processes, they perform computation in parallel. Then they do some blocking collective in this first example, and then they perform more computation. In a non-blocking version of the same code, I would do P processes again computing, then I would launch a non-blocking collective, they would continue computing while the non-blocking collective is working, and then I would synchronize these processes, essentially decoupling synchronization from the data movement itself, and then I would perform the computation at the end. So that is relatively easy to understand, so there's nothing to write home about. It's a factor of 2 speed up you can get. And back to Sidney Fernbach. So he was rightfully stating at the time that the operating system should not have an impact on the speed of the machine. Ideally, yes. Well, I completely agree. unless it does have an impact. And great researchers led by Fabrizio Petrini in SC23 were publishing a paper about the case of the missing supercomputer performance, where they realized that the operating system did have an impact on the performance of application by small deviations that were eventually propagating to wider, through collective operations, to wider slowdowns. So what we did later is we actually looked at this phenomenon that this team of researchers found, and Word says that it was a printer driver running on those machines, but I cannot be sure here. We looked at this in greater detail, trying to understand the real effects of those slowdowns, of those small slowdowns. Because at the time, there was the Jaguar system. And the Jaguar system had an interesting observation. There was an interesting observation that some applications would not scale beyond 15,000 or 16,000 processes. Only some, not all. And it was an interesting challenge to figure out why. And we later discovered that these applications were actually hindered by small delays on single nodes. And here you can see a trace of these small delays, sometimes 10 milliseconds. Well, 10 milliseconds is not a whole lot, but if that propagates through a collective operation to a larger set of processes, as you can see here for the all-reduce operation, where the red line is the noise-free execution, and the green line is the execution with injected operating system noise, or the green box plots. So you can see these box plots actually being not really relevant with less than 16,000 processes, but then there's a phase change going on, where if you have more than 32,000 processes, you get a deterministic slowdown of the application of about 50 times. And this was essentially meaning that some applications like conjugate gradient would simply not scale further. They would in fact run slightly slower. So now you could argue that we could use non-blocking collective operations that decouple the synchronization, which causes the slowdown, and the communication, which is of course necessary to deal with that effect. And we could also argue that the operating system should fix these issues, which Cray very quickly did afterwards. But then there are new issues today, like, for example, multi-tenant cloud systems, where it's not so easy to fix the interference with other tenants. I mean, you cannot just remove them from your cloud system. So these become important again. There are many other contributions that we could talk about, but I don't want to go into this in detail. But I would recommend you to look at our MPI, using advanced MPI book that Bill, Rajiv, and Rusty, my co-authors, and may Rusty rest in peace, have written over the years. And also you could come to our MPI tutorials, and actually that was just given on Sunday, so you could look forward for next year, I suppose, which we are probably giving again. But now, let me go back to these major technology shifts. I actually did not tell you about yet what these technology shifts actually were. So one of those, probably the most relevant one, I would call the RDMA revolution. Again, going back to the 80s, the prevalent networking of choice was Ethernet with sockets. The coherent memory access, or scalable coherent memory access, was another interface that was introduced shortly after, even though in my opinion scalable and coherent doesn't really work together, so it shouldn't be used in one sentence. And thus it was quickly replaced by active messaging based systems. We all know Myrinet operating system bypass. We know Quadrix, that was one of the first to popularize protocol offload. We know the virtual interface architecture with zero copy. And Cray Gemini was unifying many of those principles into a very elegant interconnect. And then came InfiniBand. InfiniBand popularized the notion of all of those under the name RDMA, Remote Direct Memory Access, with the interface of InfiniBand verbs. There was quickly a criticism coming up that Remote Direct Memory Access actually does not fit the semantics of MPI message passing very well. And if you think about it, it does not. It's simply memory access versus matched message passing, in-order matched message passing. And we will get back to that later. So now came the IBM Perks topology. We had the Open Fabrics Alliance standardizing many of these RDMA interfaces, Portals 4 extending those, and then Rocky and libfabric going towards a wider adoption. So in some sense, RDMA conquered supercomputers. Most of today's supercomputers are in fact running RDMA, if not most, if not all. Even the data center computers are starting to embrace RDMA, the mega data center providers. Google, Amazon, as well as Microsoft are admitting in one way or another to either seriously think about or even deploy RDMA systems at large scale. So back to Sidney Fernbach, who says if you have an underlying system, you need to really be able to exploit it to the greatest extent. Okay, well, what we had to do in MPI is now modernize the MPI-2 interface to make it adopt to the new hardware changes that were happening over those 10 years. And so we succeeded in doing so, but we were really following somewhat Sidney Fernbach's advice without knowing, and looking at the greatest detail of how to communicate. For example, for that paper in the lower bottom, we looked at the number of cache misses required to transport data from A to B. And we somehow proved that our implementation that had the lower bound of cache misses was optimal, in this sense, on that particular system. So that was quite nice. And we actually showed communication latencies of 1 microsecond across a very large system, the Blue Water system at the time. Today, communication latencies are higher. Communication latencies go up over time, which is also an interesting insight. We also managed to run large jobs on 500,000 processes, delivering speedups, application speedups of more than 10%. So that worked. But yet, networks felt somewhat slow. And then we looked at the topological structure of these networks, trying to understand, well, what does the connectivity of these switches and endpoints actually mean? And you can plot nice plots, various networks with using the dot tool, and this is really just the topological structure. But all of those have one thing in common. All systems use, or all of those systems on the slide, use expensive non-blocking folded clause topologies that are also sometimes called full bandwidth fat trees. So full bandwidth, right? But unfortunately, none of those systems was actually delivering full bandwidth. Then back to Sidney Fernbach, who was always living in the same environment that I was in very often, between vendors claiming things and you actually measuring things. And we all know in the HPC community after the 12 ways to fool the masses that this is not always resonating or not always matching each other. So what we realized is actually that this bandwidth loss comes from the fact that we are statically routing these network topologies. So in theory, there's one communication pattern that works, but we will never hit it in practice. And if you now look at the set of random communication patterns, just sampling random communication patterns from the full permutation, you find that already with 128 processes, you're expected to have less than half your bandwidth on a statically routed fat tree with 512 endpoints. So we fixed this with adaptive routing in 2008, one of the earlier adaptive routing analyses with Myrinet at the time. And we were able to achieve nearly the highest bandwidth. Today, most supercomputers, if not all serious supercomputers, are using adaptive routing in one way or another. So then we moved on and looked at different topologies, because while we did this work, we realized, oh, this is interesting. These folded clause networks, they're actually quite inefficient, because you realize when you do this adaptive routing that you don't really need all those links. So lower diameter topologies were moving forward. And one was already in the design phase, which is hierarchically fully connected topologies. Like we all know the Dragonfly, all of the exascale topologies today, exascale machines are using that Dragonfly topology developed by Cray originally. I was part of the Blue Waters team working on somewhat of a competitor, the Perks computing system. Unfortunately, not a wide technological success, mainly for business reasons that some of you have seen. But very similar idea. And from there we went forward and said, well, why don't we take this idea to the extreme? Why don't we go from a low diameter topology to lowest diameter topologies? And together with my student Maciej Besta, we developed a topology that was really the lowest possible diameter, diameter 2, because if it's diameter 1, you only have a single switch. Okay? So there were more diameter 2 topologies later that we looked at. There was this week at the conference, just yesterday, collaborators from Intel, led by Kartik and Fabrizio, were actually looking at extending the SlimFly topology, extending the idea of diameter 2 to more variants and slightly better properties. And another work that we also talked about at this conference, also yesterday, topologies specialized for particular communication characteristics of applications. Like deep learning is all the rage now, so we have a topology that just works specifically well for deep learning. So with that, I'm getting to this week's conference with my overview. So what I want to spend now some time on is how do we go into the future? So there will always be a need for faster computers, as Sidney Fernbach said. And my deep belief is that the future will be data. So we have to think about data. How do we work on data? We have to think about data movement operations. So really, we have to move our way of thinking from floating point operations to what I would call data operations per second. So this term is new, DOPS, it sounds like flops. But it's very, very different in the sense that we really count what we do to move data and not just what we compute. Furthermore, I believe that we need to look into data-driven modeling and large-scale artificial intelligence systems to understand data as it moves, to look more at the semantic properties of data. And I believe that much of this will be driven by smart networks and smart communication in one way or another, which already today is used in cloud computing and mega data center environments, which I just want to briefly highlight. So we found that networking in mega data centers and high-performance computers is essentially already converged at level 0. So we're using very similar low-level, or the same low-level technologies. And I'm predicting that the same convergence will actually move up. So layer 1, layer 2, potentially layer 3 will be the same in data centers and supercomputers as we know them today. And we need to see how we navigate that space to not get lost in this transition. If you look at cloud HPC or on-prem HPC, performance today, latency at the top and bandwidth in the main plot, left side cloud HPC, right side on-prem, you see that they're already somewhat comparable in terms of latency and bandwidth. So some are faster, some are slower, some are much faster on the cloud side in terms of latency, but bandwidths are generally comparable. So this is going to be an interesting ride in the sense that I would claim that the economy of scale of mega data centers will drive the hardware that we have to use in some sense. So we will probably not have much choice. And this is maybe a sad statement, but I think this is an opportunity for us to also influence the mega data centers on that side. So I'm hoping that we are moving beyond RDMA networks towards smart networks, towards smart NICs like they're already deployed today in the HPC context. And let me explain you what I mean by this, what I mean by smart NIC with a little metaphor. So we've all understood how compute acceleration has changed our community in fundamental ways. So we went from shader languages in the good old days, OpenGL, DirectX 11, through a process of generalization that really revolutionized acceleration, really started the AI revolution, as some people claim. So enabled us to use massive computation through the development of CUDA, OpenCL, and later OpenMP4. So this was really a massive phase change in our community. What I believe is that we should look at this phase change not just for compute acceleration, but also for data acceleration. Because if you're looking at networking today, we have things like P4 and eBPF, which are very similar to shader languages, very, very simple, highly specialized packet processing frameworks. And I believe that a process of generalization, very similar to the CUDA process of generalization, could lead to a framework that allows us to do data movement acceleration, data processing acceleration. And our proposal for this is the SPIN framework, streaming processing in the network. So going back to Patrick Joffrey's critique of RDMA, which is a semantic mismatch between RDMA, memory accesses, and message passing. And we could address this in the NIC. We could translate these protocols directly in the NIC from 1 to B. And this means we free the CPU from those tasks. And we believe that the streaming processing in the network idea, together with fully programmable packet handlers, will actually enable this movement to have a seamless protocol translation from whatever is on the wire to whatever we need at the application level. With that, I would like to close my discussion on networking and move on to data movement in computing. So here I want to start with Mark Horowitz, who in 2014 at ISSCC looked at a simple 45 nanometer process. He analyzed how much an FP32 addition would actually take in terms of energy. It's about 1 picojoule. Just loading the 2 operands from SRAM, from on-chip memory, is 100 times more expensive. Jack had a very similar analysis yesterday. But loading it from DRAM is more than 1,000 times more expensive. Yet, in our community, we continue to think in flops per second. And I'm wondering why. Well, one of the answers may be because it's very, very simple, because it's just the simplest to analyze. We can very easily count flops. Well, to give you an example, how many flops are needed to multiply 2 n by n matrices? I mean, many of you immediately have the right answer in their mind. It's n cubed, right? But now, let me ask you a slightly different question, which is not that simple, but very much related. How many data operations are now needed if I have a cache of size S to perform this operation. Data operations are load stores from memory, so you can count those, right? There are I/O complexity measures for this. But the answer is not that easy, and I'm pretty sure that most of you are probably not getting to this answer quickly. It's n cubed divided by square root s, of course, asymptotically. The square root s comes from the volume of a tile, which is square root s by square root s. So we again have this problem that the I/O complexity is significantly harder to analyze than computational complexity. So going back to Sidney Fernbach, he also recognized this back in the days, that a local memory is extremely important for computation. And this computation will just be sped up by increasing that local memory size and using it more efficiently. So we've been doing this in the recent past by looking at matrix multiplication, matrix factorization, and just this week, again, tensor contractions, optimizing I/O movement and data movement, and leading to higher speedups and leading to higher efficiency at the end. So I want to also quote David Patterson, because now we have to see how are we going forward, how will we be moving forward? Well, he says logic improves much faster than wires, even on chips, meaning that the situation will just get worse. The situation will not get better in the future, unfortunately. So I'm claiming that we do really not understand today, unfortunately, how to reason about I/O efficiency in real programs. We understand how to reason about I/O efficiency in algorithms. As I told you in the previous slide, matrix multiplication, we understand factorization. But real programs, if I give you the source code, is much harder to reason about. So many of you will see the source code is just a matrix multiplication, but let's assume we don't know what it does. What can we do if we get a source code that we don't know what it does? Well, we can run it. We can run it, we measure with PAPI, for example, the execution time, the flop rate, and the memory bandwidth. Right? So we get these numbers, this is great. This code is semantically equivalent. It's just a tiled version of this matrix multiplication, very much like Jack was talking about yesterday. Well, again, what we can do is we can run the code, we can time it, we can get the gigaflops per second, and we can get the memory bandwidth. One interesting thing we are seeing here is that the write code is running faster, and now it's not advancing. The write code is running faster, but has 10 times lower bandwidth. So it gets a higher flop rate, but actually the rate, the effective utilization of the memory is less, because I'm getting less memory operations, less data operations per second. And many of you are immediately seeing what's going on. Well, of course, this code has been optimized to move less data. While the left code moves about 1 terabyte of data, the right code, due to the tiling and cache locality, moves significantly less data. So for this, we defined a new metric, what we call the memory use efficiency, where we really looked at the I/O efficiency separate from the bandwidth efficiency. So we cannot just count memory operations per second like we count flops. Like, we have to look at, first of all, how effectively are we using the memory operations, and then we look at the flops. So we combine the I/O lower bound with the measured bandwidth. 2 factors. In the DAYS project in my group, we're looking at how to apply this to real codes at a in a wider setting. And you should check this out, and you can actually use that. So with that, I would like to conclude my talk and thank you all to be a perfect environment for young scientists like me for doing their research. Specifically, I want to thank my many mentors who have helped me to strive in that community and to navigate the space and really understand how to move forward. I also want to thank many of my collaborators and friends in the community going forward and understanding understanding how to deal with various aspects of technology, but also personal things. And last but not least, I want to thank my many group members who have been fearlessly implementing my sometimes crazy or out there ideas, but they have been working hard and helping me to succeed, and also making our group very, very successful in the community. So with that, I would like to close with one call to all of us. We should change the way we think and teach efficient algorithms to undergraduate and PhDs, really in the sense going to I/O complexity, to data movement. If you want to join, let us know.
Thank you, Torsten. We have time for a few questions. There's one there.
For the blue water system, I don't know why they are sporadic non-compute nodes, but when I removed the fragmentation of network allocation, I was able to improve cybershared code by 35% faster. And so can you comment about the fragmentation in allocation, how we can eliminate that? Another thing is all these different low diameter topologies, I'm trying to make it have a hop in the actual data movement in average. So are we gonna ever get back to hypercubes with the optical connection?
Yeah, so thank you. The first question was on the defragmentation on torus networks, essentially. The blue water system that was deployed, not the one that I was working on, was actually a torus system which had the problem of fragmentation. Yeah, this is hard to solve in practice, as you point out, and yes, you get high speed ups if you solve it. There are new topologies that can actually avoid this fragmentation problem, and I would recommend you look at this Hemming mesh topology, which is somewhere in between a mesh and a fat tree network. So to the second question, if you're going back to hypercubes, I believe these lowest diameter topologies are more cost effective if we understand how to route them and how to actually wire them in practice. This is still an open challenge. They're not widely deployed yet, but they are about 30–40% more cost effective under this scenario. So research is continuing there.
Topology aware and also algorithm specific, so I would appreciate any collaboration. Thank you.
Thanks.
Hello, thank you for your talk. My name is Diego Roa. I'm from the University of Delaware, Capsule Laboratory, and the ANL Argonne. My question is, do you think there is a better way to describe the programs that makes more clear the data movements that are implied? And if so, do you think we will see hardware layer support for these kind of operations?
So sorry, describe the programs to see what? Sorry, I did not understand.
To make more clear the data movements.
I see. Oh, that is an interesting question. Yes. So is there a way to describe programs better to have explicit data movement in there? I believe yes, and there are many approaches that already take advantage of this. For example, in the polyhedral model, you have a very nice overview of how data is moving. If you just use a DSL, like the DynSum example we have, that only allows certain operations, that gives you more structure, then you understand what the data movement can be. The more general you go, like if you're in C, for example, allow pointers, then you will not be able to, to understand what's going on. So we somehow have to find the right way to express these data movement operations more explicitly. And this is part of the research we do in this DAYS program, where we try to really model data movement explicitly. Very good question. Thank you.
Right. All right. Let's thank Torsten again.